Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 3 for this week. And this is a bonus video that ended up taking a little bit more time to produce than I had counted on. But I thought you might be interested in learning about how differences in latitude and differences in how high in the sky the sun is can make a huge difference in terms of temperatures across any part of the world, and how it can contribute to severe weather potential during the course of the spring. And so that's going to be the basic topic for today. So let me click up here. Now there's a group out at Oregon State University, and they have a program called PRISM. And they have done a phenomenal job of taking all of the normal or 30-year average temperatures and basically creating graphics, very detailed graphics for, actually now they're doing it for every day of the year. They used to do it for months, but now you can do it for any day of the year. And so these are the normal high temperatures for December 21st. And the legend down in here, I don't know exactly why they did this, but they broke up the colors in 3 to 4 degree intervals. Now I want to move on to January, and I'm going to count the number of colors here, okay? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 different colors. So a lot of temperature contrast there, okay? From northern Minnesota all the way down to southern Texas and southern Florida. Now, as we move on ahead in time, here's February 21st and here's March 21st, do you notice how that packing of colors shifts northward? Okay, in January it's down near the Gulf Coast, but then it starts to shift northward by the middle of March. And basically what's happening there is that the sun is getting very strong in the southern part of the United States, but it's still fairly weak up here across near the Canadian border. And so you're setting up this big zone of temperature contrast in here, which of course is a breeding ground for big storms and can be the harbinger for severe weather, tornadoes, damaging winds, and all that type of thing. But then finally, as we move deeper into the spring and finally get to the first day of summer, now how many colors do we have? 1, 2, 3, 4, 5, 6, 7, and then if you count some of these colors here in the desert Southwest, you might get up to 10, but obviously a lot less in the way of temperature contrast from north to south across the country. And the days are actually longer the farther north you go once you get into the later spring and summer period, which is something that a lot of people don't realize. Okay, so why is that? Why does the temperature contrast decrease as we head from the winter on into the spring and the summer? Well, I'm going to have a little bit of math here. Think of this as being the Earth, okay? And we're going to create what we call a right triangle. And a right triangle means that one of the angles has to be at 90 degrees. So that's going to be the one there. And then we're going to say this angle is 30 because that's what would correspond with 30 degrees north latitude, okay? And we're going to say that the radius of the Earth is 1 unit, okay? Whatever you want that to be, it's just 1 unit. So the sine of an angle is defined as the length of the opposite side from that angle divided by the length of the hypotenuse. Well, what the heck is the hypotenuse? Well, that is the side opposite the right angle. So where's the right angle? Here. What's the opposite side of that? This 1. Okay, so that's the hypotenuse, this thing here. And then the opposite side to 30 is this side here, which is 0.5. And if you're interested, the other one is 0.866. So the sine of the angle is the opposite side, 0.5, divided by the hypotenuse, 1, or 0.5, okay? Now, let's go up to 60 degrees north latitude. We've still got a right angle, but now that angle is 60. We've still got our 1 unit of the radius, that's the hypotenuse. And so the sine of 60 is the opposite side, which in this case turns out to be 0.866 divided by 1. And so the sine of 60 degrees is 0.866. Now, I also need to mention that the sine of 0 degrees, which would be the equator, is 0. And the sine of 90 degrees, which is the North Pole, is 1. Okay, so with that in mind, From 0 to 30, the sign increases 0.5. From 30 to 60, it only increases 0.366. And from 60 to 90, it only goes up 0.134. So the point I'm trying to make here is that at the lower angles, okay, that's where you get the most bang for your buck in terms of the increase in what the sign is, okay? And it turns out that incoming solar radiation is going to be proportional to the sign of how high in the sky or how high above the horizon the sun is, okay? Or you can say it's proportional to the sign of the latitude as well. One other thing I have to mention here before I get to some actual numbers. There's something called the sun's declination angle, which is a really fancy word for how far north or south the sun gets with respect to the Earth. On the first day of winter, December 21st, it's directly overhead at 23.45 south latitude. So it only gets to about 30 degrees above the horizon here in Raleigh. But in summer, June 21st, it's at 23.45 north latitude, which means it gets to within about 12 degrees of being directly overhead. So it makes a big difference in where the sun appears in the sky. So here is a table. Let's take this column by column. This is the date here, going in monthly intervals from December to June. This is the declination angle. So the sun starts off in the southern hemisphere, crosses the equator March 21st, and then gets as far north as it's going to go on June 21st. So this is the sun's elevation angle above the horizon at 25 degrees north latitude. So on December 21st, it's 41.6, and then it increases to 65 by March 21st, and by June 21st, it's almost directly overhead, okay? Almost. At 50 degrees north, it's only 16.6 degrees above the horizon. This is up near the US-Canadian border on December 21st, and then 40 degrees by the first day of spring, and then 63.4 by the first day of summer. So there's still a 25-degree difference here. Okay, that doesn't change. That difference is the same no matter what date it is. But if you take a look at the fact that the biggest change you get in the value of the sign is at the lower angle values, look at this. The difference in the directness of the rays, of the incoming solar radiation, between these two latitudes on December 21st is 37.8%. Okay, that's really big. But as the sun gets higher in the sky and the angles get bigger, then you don't get as much of a jump, okay? And so by the time we get to the first day of June, or the first day of summer, or June 21st, the difference in the directness of those rays, or the amount of incoming radiation, is only 10.5%. And so you can see why you would have a lot of temperature contrast in December and January, because the amount of incoming radiation varies by a significant amount from 25 to 50 degrees north. But by the time we get to June 21st, then that difference is much, much smaller, because all the angles, all the elevation angles above the horizon are significantly larger, and the sign does not increase as quickly at those values. And so the temperature contrast is less, the severe weather potential is less, and everybody is warm in June, just to slightly varying degrees. Okay, I hope that made a little bit of sense. And so we are headed into that core of the season right now, where the temperature contrast is going to be, pretty high across the country. And so we'll have to see how our severe weather season turns out. All right, that's it for now. That's bonus weather video number 3 for this week. And we will be back again on Monday with the next daily update and the next bonus weather video. Have a great Friday evening, what's left of it, and an even better weekend. And we'll talk to you in about 3 days. Take care, everybody.